Alright, taking a look at part 2 here. We're looking at a different set of reactions now. A different electrophile. We've been using H plus as an electrophile. Right? H plus in the form either from something like HBr or HCl or even HI or H2SO4. But now we're going to change our electrophile. We're going to use BH3. Right? We talked about boron being an electrophile because it doesn't have a complete octet. Right, so it's similar to a carbocation in that regard. But because it doesn't have a complete octet, it would be a good electrophile. So what happens here, so let's look at our net reaction. We call this a hydroboration, boron, hydrogen, oxidation. So what happens is you add an H and a Br across a pi bond, but then you change out and get an alcohol. So it's similar to that reaction we did with H2SO4 in water, where we also got an alcohol, right? And this was a catalyst, so we regenerated that. So we also get an alcohol. This is a little different mechanism, different electrophile, and there's another part that's going to be different as well, especially when we look at an unsymmetric alkene. So net reaction, we have hydroboration, add an H, add a Br, and then we oxidize it so we get an alcohol. Right here again is the picture again. That's kind of drew again. H2SO4 in water, you get 2-propanol. The oxygen OH is the nucleophile. We've done that mechanism before. Now, if you take the same reaction here, if you number these carbons 1 and 2, you'd probably notice, right, those carbons are different. When we use H2SO4, we get the group, the OH, on the more substituted carbon, right, because we go through this one has a carbocation. We go through a carbocation. Now if you look here, all of a sudden the OH ends up on the less substituted carbon. Now that would probably tell you what? No carbocation, a different mechanism. Right? So with BH3, no carbocation. So what does that mechanism look like? This is the mechanism. It all happens in one step. So your pi bond attacks the empty orbital, the empty p orbital of the boron. At the same time, the hydrogen goes to the other carbon. Now, why does it do that? Right. So imagine the boron's pretty big. You want to get the boron's going to end up being bonded to the less substituted carbon. Right. This is the less substituted carbon. We did 1 and 2. Right. This carbon's bonded to only one carbon and 2 H's. This is bonded to another carbon. So the boron bond attacks the empty p orbital. At the same time, this H breaks and attacks that carbon, right? And they add in such a way that they're cis. Right? It all happens at once. 2 arrows moving at once. Pi bond attacks. At the same time, this BH bond becomes more electron rich, and that attacks. Right. So within the molecule, right, you have an electrophile. Right. So you have a nucleophile attacking this electrophile, which then creates this electrons into a nucleophile to attack this before a carbocation forms. So no carbocation. This all happens at once. One step. So it's a one-step reaction. Right? To get to here is a one-step thing. Now, that's another picture of this, right? We talk about why does it go. The boron wants to be attached to the less substituted carbon so things get away from each other. Whereas in HBr, right, we want to have the more stable carbocation. Right? Addition of BH3 has no carbocations. The boron wants to be attached to the less substituted carbon. Think about steric hindrance. Things want to be away from each other. Where here it's all about having a very stable carbocation, different mechanism. Right. Another thing nice about BH3 is BH3. So right, we're adding H. So there's 3 H's. So if I have one of these, right, BH3 has 3 H's. So it actually can react with 3 of those. Right. So you could actually have this in you need 3 alkenes per 1 BH3, right? So the equivalence is there. It's an interesting question, right? So there's 3 H's. You can actually use it to react 3 times with 3 different alkenes. So what happens in the second step, you probably noticed before, there was step 1 where the boron and H add. That's the hydroboration. Boron goes to the less substituted carbon. Then the final step is an oxidation, right? You don't need to know the mechanism for this, but all you need to remember is that you're just going to replace. Straight up substitute BR2 with an OH. So that's substituted. And that gets the alkene, or the OH, on the less substituted carbon then. Right? Like I said before, no carbocation rearrangements. You should notice that because there's no carbocations, there's no rearrangements. So you can start to react like an alcohol, an alkene like this, where before, with HBr, we noticed that if I put a plus charge here, there'd be a hydride shift. Here, if I put a plus charge here, there'd be a methyl shift. But since we don't go through a carbocation, that isn't even a problem. The boron adds to the less substituted in the first step, and H goes to carbon 2. The boron adds to carbon 1, the mechanism I showed before, the less substituted carbon. And then in the second step, what the boron would be right here, we replace that with an OH. But there's no carbocation, so don't worry about rearrangements. Now shifting gears again, let's look at this reaction. Right? So now we've done HBr, H2SO4, we've done a reaction with BH3 to get the OH on a less substituted carbon or pi bond. What happens if we react an alkene with Br2 or Cl2? Now we get Br2 adding across the pi bond. We get 2 new carbon bromine bonds, or we get 2 new carbon chlorine bonds. But this is kind of difficult to think about because we've been talking about, right? The pi bond is our nucleophile, but that would mean that something like Cl2 would have to be the electrophile. And that's maybe weird to think about, right? We think about chlorine being very electronegative. But don't forget, right? Think about the size of our chlorines or our bromines. Right? These are big molecules, right? Big fatties. Right? At any point, as the electrons kind of sloshing back and forth, maybe at this fat end could be a little delta plus. Maybe all the electrons are over here today for a second, and all of this over here is kind of delta plus, right? They're kind of sloshing back and forth. So we know the pi bond is the nucleophile, but we got to think about the chlorine kind of being the electrophile. It's a little different. But again, it looks to me no carbocation rearrangements as well. So what does this mechanism look like? Again, no carbocations, or no carbocations, which of course means no rearrangements, which is nice. No rearrangements. So this is the mechanism looks like. The pi bond attacks the bromine, the Br-Br bond breaks, and at the same time a lone pair comes back down and clamps down. So it's 3 arrows. So you think about the pi bond attacking so pi bond attack, the electrophilic Br, bond breaks, Br minus leaves, and then the other bromine comes clamping back down. Now some of you might say, well, how do you know this happens? We know this happens because we don't see any rearrangements, so we can't have a carbocation. So we know this bond has come back clamping down. So at the same time, now we've made a little cyclic bromonium ion with a bromine with a plus charge. This is pretty reactive. The other bromine can come back in now and attack and kick up those electrons. And that's how you get the 2 bromines. Right, that's how you get the 2 dibromal compounds. This is just showing, right, cyclic bromine is pretty reactive, right? It makes those carbons, right? If we look at that, just because, right, again, this is one of those cases where, right, we put the plus charge on the bromine, but really, where's the delta plus at? It's really delta plus on the carbons. The Lewis dot structure is kind of lying to us. Right? Again, because we go through that bromonium ion, right? No carbocation rearrangements. It's easy, it's nice. No carbocation rearrangements. So if we don't have a carbocation, no hydride shifts, no methyl shifts. Alkenes do not add I2. Right? This is just for this case, so I2 doesn't work for a variety of reasons. It's an unstable molecule, so I think usually they're sensitive to light, so you don't need to worry about I2. Now what happens if you have Br2 or Cl2 and you have it in a solvent? Now remember our beaker analogy, right? A solvent in our beaker, there's always lots of it. So let's say you make your bromonium ion, right, like we thought we were going to, in this case, and we made our Br minus, right, we balanced our charge, and I would say Br minus, right, it's a very good nucleophile, it's electron rich, right, it's a better nucleophile than water would be. The problem is concentration matters. So, right, yes, Br minus is a better nucleophile, it's more likely for it to attack. But what happens is it doesn't, because let's say there's a million of these waters around, right? There's a million of these waters around. Then it just becomes a numbers game. The water is more likely to attack. The water is more likely to attack just because, right, in the beaker, you got a lot more water floating around. So it's more likely for it to attack. Now there's another step here amongst us to think about. This is, we call this carbon 1, and this carbon 2. Right, it didn't matter before as much because we had BR and BR, right? There's no difference between carbon 1 and, bromines go on each one. Now all of a sudden you notice over here, wait a second. Where does the bromine, where does the OH end up at? And the OH ends up at carbon 1. And the bromine's on 2. Now why is that? Why is the water, right? We said it's a numbers game, but why is the water more likely to attack that carbon, right? In this case, this is 1, this is 2. Why might we think it's more likely to attack carbon 1? So why might it be more likely to attack carbon 1? So there's another mechanism example here. So there's carbon 1, there's carbon 2, 1 and 2, 1 and 2, 1 and 2. So the first step is going to be slow, right? Making this bromonium ion is pretty unstable, right? It's going to be a slow step. So if we made a free energy diagram up here, all right, E. So we start with star material. It's going to take a lot of energy, right? This is SM. This would be intermediate A, intermediate B, and our product. All right. Intermediate A is pretty high in energy, right? It has a bromonium ion, that makes sense. Intermediate. So what happens though? Why do I attack carbon 1, do you think? Well, this carbon has more substitution on it. It's more likely, like just we talked about carbocations, more substituted carbocation has more hyperconjugation buddies, so it makes it more stable. This carbon can handle the, what I like to think of it, that can handle the delta plus ness, right, more. It makes this carbon more delta plus. That carbon is more delta plus, and that's where the water is more likely to attack. Right? There's a lot of water around, so that's why water attacks versus bromine. And water chooses 1 versus 2 because 1 is actually more delta plus, because it can be. It's more substituted, right? More substituted. Because it's more substituted, it can be more delta plus, which makes it more electrophilic, so the oxygen nucleophile can attack and break that bond. That's why it attacks the more substituted carbon. Now, the next step is fast, right? We want to take, there's a lot of water still floating around, we don't want to have charges, so we get rid of that. The oxygen takes that H, gives those electrons to the oxygen back. You make a little acid, right? So water removes that proton. Right? So the second step would be super fast, right? And that's pretty stable. Int B, and then finally get to our product. Right? This is our starting material. So again, transition states. Every arrow represents a transition state. Right? Every arrow represents a transition state. Intermediates are the valleys, so they're fully formed bonds. So bromonium ions we've seen. A lot of water around, more likely to attack, even though it's not as good nucleophiles, BR. And because carbon 1 is more substituted, it can be more delta plus, oxygen is more likely to attack there. Now this last little step is just getting rid of the charge, right? You can just have this leave by itself, right? You make a little H0 plus, and now you make your product. Right, this is just showing it. Why does it follow a different rule? Because again, this carbon can stabilize, right? If this is carbon 1 still, this is 2, the more substituted one can stabilize the delta plus more, right? Just like it does for carbocations. That's when it's going to want to bond to. That's the most delta plus carbon. The more substituted, the more delta plus. So that's where it attacks. Other reactions, right? This is just simply changing things around. What if you use alcohol, right, instead of water? Right, then the oxygen of the alcohol will attack. You make an ether, right? You make an ether, right? Common mistakes I'll see. People want to, if there's an alcohol, you're making an ether, right? Don't try to break this carbon-oxygen bond. NaCl, you can put that in there, put a bunch in there, maybe get the chlorine to add, right? Again, to the more substituted carbon. Just little different things in there, but check out. Make sure you're wary of the solvent. It won't always be water. One final thing for this part, there's something called an epoxide, where again you take an alkene and you make a 3-membered ring with oxygen. We call that an epoxide. So we use something called peroxy acid and a carboxylic acid. And it's interesting because peroxy acids have this kind of weird looking OO bond. Right? We already know, right? Our alkene is our nucleophile. Right? So it's kind of, again, that kind of strange thing where, well, one of these oxygens is going to have to be the electrophile. It's kind of like that BR2. Right? So let's take a look at that mechanism. Right? So there's a weak bond, right? So that's a weak bond, right? That kind of, think about that sloshing the bromine back and forth, right? One of these oxygens is going to be kind of delta plus. Right? Usually we use something called MCPBA. So there's a picture of that. It's just a particular type of peroxy acid way to make epoxides. Here's my mechanism for you. So again, right, it's similar to the addition of BR2. The pi bond's the nucleophile. It attacks the oxygen. You need to break the oxygen-oxygen bond, just like you broke the bromine-bromine bond. Electrons go there. The pi electrons take that H, which then is delivered, these electrons get delivered to that carbon. Right? The easy thing I want you to do is, again, you want to number C's, add lone pairs, right? And one, you want to do bonds broken, bonds formed, right? What bonds need to be broken, what bonds need to be formed. So take that time to go through here and look at bonds broken, bonds formed. Number your carbons, number the oxygens too, I would add, right? Might as well make NOs, right? Number everything, add the lone pairs in. What bonds must be formed, what bonds must be broken, right? From here to here. It's very similar to this. So that concludes part 2.